Welcome back. Any electrochemical double layer capacitor needs to have high surface area, and this is achieved by introducing porosity in the electrode. So we would be looking at porous electrochemical double layer capacitors in this lecture. We have already looked at porous electrodes via a series of lectures. So please refer to this lecture wherein we introduce porous electrodes in the context of batteries. The concepts are fairly similar when you consider porous electrodes in battery, capacitors, as well as fuel cell. So it's good to understand what has been previously done. So a general porous electrode is modeled via the following circuit. We have the current collector on one side. So we have a porous electrode of a finite thickness. On the other side, you have the electrode which is facing towards the electrolyte. So there is a current separator in this case. And within the porous electrode, there can be different resistances. This refers to resistance in the electrolyte. This is the resistance faced by the ions as they flow inside the electrolyte of a porous electrode. Rs refers to the resistance for the flow of electrons in the solid part or the electronic conducting part of a porous electrode. Then you may have the interface between the electronic conductor and the electrolyte with its own capacitance that is indicated by double layer capacitance, and there can be resistance to charge transfer uh, when there is a reaction, Faraday reaction occurring between the ions in the electrolyte and the electronic conductor. All these things were introduced in this lecture. Please refer to this lecture to get additional clarification. So in the context of batteries, the question we were addressing, what is the current in a porous electrode as a function of the following quantities. The electronic conductor will have a potential distribution, and the electrolyte within the porous electrode will have a potential distribution, and there can be a concentration distribution within the electrolyte within the porous electrode. So as a function of all these quantities, we were addressing the current response of a porous electrode in the context of batteries. So we would like to look at similar questions in the context of capacitor in this lecture. So the current in the electrolyte is given by a simple Ohm's law kind of behavior. So conductivity times gradient in potential. So 2 refers to the electrolyte, 1 refers to metal. And then we did a charge balance taking into account the Faraday reaction, the context of batteries, and we neglected charging of the double layer because we were only interested in modeling current distribution of a porous electrode of a battery. And this charge balance led to this equation. So all these terminologies are clarified in this lecture. Please refer to this. So here we have two kinds of current. One is the current, which is reference to the entire cross-sectional area of a battery electrode. Then this is the area per unit volume. This is the current across the actual electrode electrolyte interface. All these things are clarified in this lecture. In this equation, we neglected the charging current, but if you want to have a more general equation wherein charging current is also included, this forms the complete equation. So this term is here. This term is modified to include the charging current. This a simple expression which we have already seen why this corresponds to a charging current across a electrochemical double layer capacitor. Moving on, when we look at a porous electrochemical double layer capacitor, we have two sets of equation. So this can be represented as a differential equation in this form. When we are looking at an electrochemical double layer capacitor without, let's say, pseudocapacitance, what we can neglect is there is no Faradaic reaction. Therefore, this term can be neglected. So this equation can be written in this form. Between these two equations, we eliminate I2 and we get a differential equation of this form from these two equations. This is a form that you must have seen in your previous classes in chemical engineering, materials engineering, and physical chemistry. This is just a form of Fick's second law of diffusion. The solution procedure for this equation is well established. We are not going to derive the solution, but we are going to just state the solution. So let us, when you are looking at a partial differential equation of this form, the first thing you do is you non-dimensionalize the partial differential equation. So how do you non-dimensionalize the potential? We have an initial potential given by phi ni, and you have a final potential phi f. And as the potential varies, that potential variation is indicated by phi as a function of t. This is the way to non-dimensionalize potential. You can non-dimensionalize the spatial variable in a straightforward manner. And then you get non-dimensional time that has certain significance. We will look at this term in the subsequent slide, but this is the way to non-dimensionalize time also. With all these three non-dimensional quantities, we can non-dimensionalize the partial differential equation. And to solve the partial differential equation, we need to have the initial and two boundary condition. The initial condition, that is that tau equal to 0, is straightforward. This would be phi ni, phi initial, therefore theta will be 0. Let's look at the boundary condition. So x equal to 0 refers to this condition. For this condition, so this is the one that is facing the electrolyte. This is the one, this part of the electrode is facing the current collector. So when at x equal to 0, theta is always equal to 1. That is, the potential has reached phi f because there is no further resistance. Therefore, this is an appropriate boundary condition for x equal to 0. But as opposed to this particular region, all the rest of the porous electrode face a finite resistance. So it takes some time to change the potential from phi initial to phi f. So we need a second boundary condition, which is given at x equal to 1. X equal to 1 refers to this interface between the porous electrode and the current collector. When we say d theta by dx is equal to 0, what we are stating is that the current density in the electrolyte at the current collector is equal to 0. We have discussed the nature of this boundary condition when we looked at modeling the porous electrodes in the battery. So please refer to uh, those lectures to get a better physical insight on this boundary condition. So putting all these things together, we will get the solution wherein we are plotting the dimensionless potential against the dimensionless distance. We will look at the features of the solution in this slide. Note, I forgot to state one thing. When we are doing all these things, what we are neglecting in this is that we are saying that this resistance is 0. All we are considering is Re, and we, as the first approximation, we are going to consider the conductivity of the electronic conductor to be infinite. Therefore, Rs is 0. We can relax this approximation. We can analyze it. That will be done in the next lecture. For now, this is 0. All we have is this resistance and capacitance because there's no Faraday reaction. Therefore, this is also 0. So within such a scenario, let's interpret the meaning of this. It is useful to look at the variation in potential in terms of current too, because to get a current, that is ionic current in the electrolyte within the porous electrode, you need to have a variation in potential. So what is the question we are interested in answering? The main question we are interested in answering is whether a capacitor, in this case, a porous electrode in an electrochemical double layer capacitor, whether it is adequately utilized. Let's elaborate on this question. So in this case, for example, when tau is a small quantity, what we see is that the potential drop is in the front part of the capacitor. Only in this region, let's say, the entire potential drop is phased. When the entire potential drop is in that manner, because the potential drop is the one that is contributing to the current, the capacitor current will be present only in only one part of the capacitor, and the rest of the capacitor is not at all utilized. So to adequately utilize the entire length of the capacitor, you need to have a potential drop across the entire length of the capacitor. For you to have that, you have to have tau as a large quantity compared to this quantity. Let us understand how to get a high value of tau. To get a high value of tau, this must be a small quantity, or you have to have a conductivity to be large, which makes sense, right? If the conductivity is large, then the resistance for the flow of ionic current within the porous electrode is less. Therefore, the ionic current is facile in the porous electrode. Other way to get adequate current in across the entire porous electrode is to have small l, right? If the thickness of the porous electrode is small, it is easy to have potential drop and subsequently current across the porous electrode. If the A, quantity A, which refers to porosity, that is the surface area per unit volume, if that is a small quantity, that means if the porosity is less, you can have current flowing across the entire porous electrode. Again, if the capacitance of the electrode electrolyte interface is small, you can have current flowing across the entire porous electrode. So that is a physical way of interpreting this condition. It would make intuitive sense, but it is good to derive this mathematically and see how the math is connected to the physical parameters. Moving on, there is an additional quantity called the penetration depth. Again, you must have seen this quantity when you looked at Fick's second law of equation. The penetration depth refers to the extent to which the potential drop penetrates in the spatial dimension. If delta is to be large, you should have greater conductivity, or the delta will become large with respect to time. So, mind you, so we are typically, when you're looking at the solution for this kind of partial differential equation, typically what you plot is phi is defined at each spatial condition. At each of these points, phi is well defined, and it also varies with respect to time, right? In time, the phi at a particular point will also change. So there are two ways to increase the penetration depth. One is to change the innate properties of the system. The innate properties, the conductivity in the electrolyte, or area per unit volume, which is indicative of porosity, or the double layer capacitance, or other way to increase the penetration depth is to just look at the system at a longer time. In time, the penetration depth will increase. In the next lecture, with this we conclude the porous electrode modeling of a double layer capacitor. In the next lecture, we will look at another important way to study the electrochemical double layer capacitance. This is via the impedance, electrochemical impedance spectroscopy for a electrochemical double layer capacitor. Thank you.